Hi everyone, my name is Zhang. Today, I'm going to present our paper accepted at the WACE 2024, D3GU, Multi-Target Active Domain Adaptation, via enhancing domain alignment. This paper aims to solve multi-target domain adaptation image classification task. Suppose we have a labeled source domain and multiple unlabeled target domains. The goal is to transfer the classification knowledge from source to the targets. However, without any labeled target samples, there is a lack of supervision in the target domains. Therefore, we propose to efficiently label a few target images using active learning. We propose multi-target active domain adaptation task. During training, we initially have all labeled source images and unlabeled target images from multiple domains. In the pre-training stage, or stage 0, we applied unsupervised domain adaptive pre-training using all available images. Then, at each following active learning stage, we train and improve the model by adding more labeled target images for training. At the first active learning stage, the model is initialized with pre-trained weights from stage 0. To select the labeled targets, we use an active sampling algorithm to sample from the pool of unlabeled target images. The active learning algorithm can utilize the trained model from the previous stage. At test time, we remove the domain discriminator from trained model and test it on the target domains. To enhance domain alignment during training, we propose decomposed domain discrimination. We use DANN for domain alignment at training stages. Parallel to the classification head, DANN attaches a domain discrimination head to classify domains. To align images from different domains, it adversarially trains the model by reversing the gradient from domain discriminator to the backbone. When source domain and multiple target domains are available, there can be two ways to discriminate domains. In the first case, we can treat all target domains as a union target domain and discriminate them between the source and the union target domains. We call this binary domain discrimination. However, since target domains are not explicitly aligned, binary domain discrimination can lead to underalignment. In the second case, we view each domain independent from the others and align them altogether, which we call all-way domain discrimination. However, since each domain has its domain-specific features that are not supposed to be aligned with other domains, all-way domain discrimination can lead to over-alignment. To achieve the balance, we propose decomposed domain discrimination, using a single domain discrimination head to trade off binary domain alignment and all-way domain alignment with an alpha parameter to properly align the domains. We also propose gradient utility to active sample target images. Suppose the green dots are source images and the yellow dots are target images. There is a classification boundary in the space. For each image, we can use its pseudo-label to compute the classification gradient, which is a red arrow. We can also compute its domain alignment gradient, which is a blue arrow. We propose to measure the image's margin contribution from being labeled using these two gradients. The image's contribution towards classification direction can be measured by the norm of the classification gradient, phi classification. When labeling an image, the only new information is from the classification label instead of the domain label. So we project classification gradient onto the direction of the domain alignment gradient and compute its contribution to domain alignment using the norm of the projected vector. Finally, we sum the two contribution scores to obtain gradient utility, phi, which can be simply used as a score for probabilistic sampling. We can also scale phi to be the likelihood for K-means sampling, which we call GU-KMeans, to sample more diverse target images. We conduct experiments with 4 active learning stages and equal budget in each stage. On Office 31 and OfficeHome, our proposed D3GU model achieves sort-of average performance in both the first stage and the last stage. We also conduct experiments on the large-scale DomainNet, where our model still achieves the best average performance. We compare binary, always, and decomposed domain discriminations in the unsupervised pre-training stage. As it shows, decomposed domain discrimination can achieve the best accuracy on most of the settings out of the 3 methods. By properly adjusting the alpha weight, decomposed domain discrimination can achieve even better performance. We further study our design of GU-KMeans. By gradually adding each component, the model can achieve better and better performance, validating the importance of each module. In this paper, we propose the first multi-target active domain adaptation framework to efficiently label target images. We aim to enhance domain alignment at both training stages and active learning stages. At the training stages, we propose decomposed domain discrimination to alleviate both under-alignment and over-alignment. At active sampling stages, we propose GU-KMeans to measure each target image's contribution towards the task. Thank you.